this lesson is looking at the behavior of structural particles. Once you get molecules built, for instance, those molecules become discrete separate units like Legos in a structure you build at home maybe, or bricks in a house. Those molecules, which are made of atoms, can be strung together, stacked together, stuck together in a way to make larger structures. But when we talk about structure in chemistry, we're talking about more than just solids. We're also talking about liquids and even gases. Yes, gas has a structure in a chemical sense. And so what we want to look at today is how once you get those particles, a bunch of these particles together, how does it affect its behavior? Physical properties, like melting point and boiling point, like the ability to conduct electricity. That's what this lesson is about. If you don't remember a lot about how monoatomic and polyatomic ions are put together, because those structures of more than one atom, sometimes if it's polyatomic, those make bricks in a larger structure. If you don't remember much about how molecules are put together, because molecules are put together with atoms that are stuck together, and those stuck together atoms in the molecule then become bricks or larger parts of a bigger structure. If you don't remember much about that, maybe you should go back and review a little bit before you watch this video. Okay, I want to talk to you about some of the structural properties of molecular covalent compounds as compared to ionic compounds. Okay? So here's several ionic compounds over here. Sodium chloride formed from sodium ions and chlorine ions. Here's calcium chloride formed from one calcium and two chloride ions. Magnesium and oxide, magnesium oxide. Now, the charge here is what these opposite charges is what draws these ions together to form a crystal, right? And so if I have a 2+ charge pulling on a 1 negative charge, that's an even stronger attraction between these two particles, or these, in this case, 3 particles. Okay? If I have 2+ and 2 negative here, that's even stronger still. Okay? So the attraction between these particles is pretty strong and gets stronger if you increase the charge. Does that make sense? Well, when we get over here to these covalent compounds, any charges that are there are partial charges. Remember? Partial charges? We talked about that? Yes? Okay. So the attraction between one water molecule and the next is not due to a complete, total positive or negative charge, but for a partial negative and positive charge. So the attraction between one molecule and the next is not as strong as that between ions. And so at room temperature and pressure, this is a solid and a crystal. At room temperature and pressure, this is a liquid, because they're not pulled together as tightly. Because solids stick together, and liquids are kind of like, they're there, and they're sticking, but they're kind of moving around each other too. Does that make sense? All right? That affects all these other properties that we're going to talk about. Okay? If we have something like these non-polar compounds, like methane here, there's no polarity at all to pull those together. In fact, any polarity that makes them stick together is called a temporary polarity. And we'll talk about that in a later unit. But so there's a very weak attraction between these molecules as compared to the attraction between water, because these have very strong partial positive and negative charges. In fact, this dips over into the hydrogen bonding stuff we talked about. And hydrogen bonding really is somewhere between being a polar attraction between one molecule and the next, and a covalent bond between one molecule and the next. The electronegativity differences between hydrogen and oxygen that creates the polarity for water is much greater than for, say, ammonia. Ammonia has is able to do hydrogen bonding, but ammonia has a sort of a less strong or less intense polarity than water does. And remember, methane we talked about yesterday. Methane is partially polar on one end and non-polar on the other end, and so its polarity and its attraction between molecules is less than that of ammonia. So you have this whole range of attraction between structural particles, and that's what we're talking about now. We're not talking about atoms here so much as we are structural particles. Structural particles are talking about things that are big enough to see. When we actually make a crystal big enough to see, the structural particles that make it up might be ions like sodium and chlorine. When we have a big enough ice crystal to see, we have structural particles of water molecules. And we're no longer talking about the attraction between oxygen and hydrogen making the water molecule. We're talking about the attraction between one water molecule and the next to make an ice crystal. Okay, the stuff you put in your tea to keep your tea cold if you're like me and live in the South. Okay? Because people in other places in the world, they don't drink iced tea much. Y'all didn't know that, did you? Y'all looking at me like you don't understand what's going on. Iced tea is not universal. Okay? Iced tea is not, they don't drink iced tea in India and China. Huh? What? Go India, yeah, okay. I thought you said you were from Pakistan. Half and half, okay. All right. I got it confused, I'm sorry. Okay. And they don't drink iced tea in Pakistan. Okay. So the point is that, I don't know what the point is. Okay. The point is that we're talking about structural particles here, okay? Structural particles, all right? So we're going to be talking about this effect of the attraction between structural particles, okay? Comparing and contrasting physical properties of ionic versus molecular, that is to say, molecular covalent properties, okay? Because molecules are made of atoms that are covalently bonded together, but not all covalent compounds are molecules. So we're trying to make sure we limit ourselves to just covalent molecular, okay? And the structural particles for those are molecules. The structural particle for ionic compounds are ions. All right. Now, be careful, because these are typical properties we're going to talk about. There are always exceptions, okay? It's not always true, it's just usually true. While most ionic and covalent compounds will behave in the manner we'll describe, there are always exceptions. So, electrical conductivity when dissolved in water. If I take an ionic compound, and we talked about this yesterday, if you have an ionic compound like table salt or like calcium chloride, and you put it in water, because water is polar and has a partially positive and partially negative end, the fully charged sodium ions and chloride ions can be separated by the water and dissolved. Okay, so they actually break up in water. Okay, we form these aqueous solutions or aqueous solutions. Okay, aqueous solutions mean something is dissolved in water. That's what aqueous means. If you have taken Spanish, you know that the word for water is agua. Kind of like aqueous, agua, okay? Got it? It all comes from Latin, all right? It's a Romance language. All right, comparing ionic compounds then to covalent compounds, when you dissolve those ions in water, you've got those positive and negative charged particles floating around there, mixing around with all the water molecules. You've got a place for the electrons to flow through, and you can have electricity flowing through water. Pure water doesn't conduct electricity very well at all. Okay, pure water is a poor, very poor conductor of electricity, as are all covalent compounds, and with a few exceptions. Okay, some of the carbon compounds can be made to conduct electricity. Actually, there's other things too, but we're going to, for now anyway, we're going to keep it simple and say it's the covalent compounds that don't conduct electricity. Okay, even when they're dissolved in water, but ionic compounds do, because those oppositely charged particles allow those electrons to move around through there, to bounce around over the positive charged sodium. Okay? So the ionic compounds break up, separate ions, give a place for the electrons to go, to flow through there, and bounce through the whole system. Okay? Molecular compounds don't dissociate into ions, and so there's no pathway for the electrons to move through this solution. Excuse me. Well, the same is true then when they're molten. When you melt an ionic compound, you separate the ionic compound into its separate positive and negatively charged ions. So there's a place for electricity to flow through. Ionic compounds then, when they're molten, when they're melted, you can put electricity through there, for the same reason that you can put electricity through water when you put one of these ionic compounds in there and dissolve it. So covalent molecular compounds don't conduct electricity very well, even if they're molten, because again, you don't have a place, you don't have any charged particles for those electrons to bounce around through. Okay? Ionic compounds break up into separate ions when they're melted, giving a place for the electrons to bounce through there, or a pathway for them to flow through there. Molecular compounds aren't made of ions, and there really just isn't any way for those electrons to flow through there. Okay, so if you try to run electricity through something that's molecular, it isn't going to happen. Those are insulators. Okay? Even ionic compounds, if they're solid, are insulators. It's when you melt them or dissolve them in water that you allow the electricity to flow through. Okay? So getting hit by lightning when you're in a tub of water, probably not so bad as being hit by lightning when you're in the ocean. All right, hardness. If ionic compounds' structural particles are more strongly held together, which one's harder, ionic or covalent? Ionic. Sure, that makes sense, right? Once you understand the underlying theory, all this stuff, memorizing this stuff is useless because you can figure it out. Yep. It's easier once you understand the underlying principle, okay, that makes all this happen. So ionic compounds are harder, covalent compounds by comparison are softer, and we're talking about covalent molecular here, not just any kind of covalent, because diamonds are covalent and they're pretty hard. Okay? We're talking about covalent molecular. We're talking about the behavior of the structural particles, molecules versus ionic ions, charged particles called ions. Okay? Ionic compounds or solids are held together by the attraction of full positive and full negative charges. Covalent compounds are held together, if at all, by partial positive and partial negative charges. Okay? Some of the partial charges are temporary. So those nonpolar compounds, they have temporary polarity. But we won't get into that until a later unit. Got all that? All right. No? You don't need to know. You don't need to know that. Just I want to tell you that everything is held together by some kind of opposite charge. Everything. Okay? Even molecular compounds are held together, if they're held together at all, into solids or into liquids by some kind of opposite charge. Okay? But it's a temporary charge on some of them. The nonpolar stuff will be temporary. We'll get that. We'll explain what temporary polarity means in a later unit. That makes sense now? Okay? All right. Melting and boiling points. Which one's going to be harder to melt? That is to say, turn it from a solid into a liquid, ionic or covalent? Ionic. Sure, that makes sense now, doesn't it? Just to define it, melting point is the temperature which a solid melts into a liquid. Boiling point is the temperature which a liquid boils and changes from liquid into a gas. All right? So ionic is going to be higher, a higher boiling point, a higher melting point, because boiling just means you're taking liquids, which are those molecules or particles are touching, and you're separating them completely. Okay, so it's still separating things one way or another. And covalent molecular compounds have a lower melting and boiling point, and it all has to do with those attractions again. Ionic solids are held together by the attraction of full positive and full negative charges, harder to pull apart. Molecular covalent compounds are held together by partial positive and partial negative charges, easier to pull apart. All right, enthalpies of fusion and vaporization. Well, that sounds like a big word, but it's not such a big idea. Let's define them real quickly. Enthalpy of fusion is how we measure the amount of energy it takes to melt something. Now, fusion is putting things together, but that's just the opposite thing, okay? Fusion is putting things together. You have to take energy out of something to get it to fuse, but the same amount of energy you took out to get it to fuse or freeze, you put it back in there to get it to melt. So it's the same amount of energy. But by calling it the amount of energy required to melt a mole of a compound, then we have a positive energy we're talking about here, okay? And not a negative energy. If you take it out, it's a negative energy. You put it in as positive energy. That make sense? Yes? I mean, you put apples into a basket. That's a positive number of apples in the basket, right? Then you put in there. Take apples out of the basket, you're subtracting apples, right? That's a negative number. Yes? Okay. Enthalpy of, first of all, the ions or molecules are stuck together when you're melting them. Melting is getting these ions or molecules to unstick and start moving around each other. They're still kind of sticky to each other. They're still touching each other, but they're just not stuck in one place relative to each other. And the amount of the enthalpy of vaporization is the amount of heat energy required to boil a mole of a compound, which means to turn it from a liquid into a gas. Okay? And so the ions or molecules of liquids are close together, touching, but not stuck in one place, moving around each other, and boiling is getting these ions or molecules to fly apart from each other. They're completely separated. So, which one's going to have the higher enthalpy of fusion and vaporization? Ionic or covalent? Ionic, yeah. Okay, for the same reason. If you understand the underlying theory, this stuff just kind of makes sense. So, ionic is going to have a higher enthalpy of fusion and vaporization. Covalent molecular would be lower by comparison. Ionic solids, again, held together by the attraction of full positive and full negative charges. Covalent held together by partial positive and partial negative charges. So it requires more heat energy to pull these ionic particles apart. The structural particles we call ions. And it requires less energy to pull apart covalent molecular particles, structural particles, because those are partial positive and negative charges, not as complete, okay? All right, simple. All you got to do is recognize the compound, all right? Which is more likely to conduct electricity when dissolved in water? PCl3 or SCCl3? Yeah, SCCl3 because it's ionic. Okay? Phosphorus and chlorine are both nonmetals, so we assume at this point in time that they're going to form a covalent compound. Where scandium is a metal, chlorine is a nonmetal, so we assume at this point in time they're going to form an ionic compound. Okay? Which substance is more likely to conduct electricity when molten? Sulfur dichloride or copper 2 chloride? Why? Ionic. It's a metal bonded with a nonmetal. Copper 2 chloride is a metal, copper, and a nonmetal, chlorine, bonded together, forming an ionic compound. And the Roman numeral kind of gives it away too, doesn't it? Because you know what those mean now. Which substance is more likely to form a harder substance when in solid form? Chromium 4 chloride or carbon tetrachloride? Chromium 4 chloride because it's ionic. Yes, very good. All right. Which substance is more likely to have a higher melting point? Iron 2 fluoride or oxygen difluoride? Iron 2 fluoride because it's ionic. Okay. Which substance is more likely to have a higher boiling point? XeF4 or MnF4? MnF4 because it's a metal, manganese, and a nonmetal, fluorine, forming an ionic compound. Xenon's a nonmetal. It's one of the noble gases. Which substance is more likely to have a higher enthalpy of fusion? SCBr3 or NBr3? SCBr3 because it's a metal, scandium, and a nonmetal, bromine. And NBr that's two nonmetals, nitrogen, bromine. Which substance is more likely to have a higher enthalpy of vaporization? Propane or table salt? Table salt. Propane is one of our one of our organic compounds, and organic compounds are almost always going to be covalent anyway. Okay, we have some salt bonds we talked about when we're talking about polymerization, but as far as naming all these other covalent organic compounds, they were all covalent, all sharing of electrons. Everybody got it? Good. It ain't hard, not if you kind of understand the underlying theory.